In this video, we're going to move on to looking at the idea of centres of mass as they relate to moments, and this is where our consideration of the idea of a non-uniform rod will start to appear. So that's where the centre of mass isn't necessarily at the centre. So for a uniform rod, the centre of mass is always the midpoint of the rod. So in previous examples, we've looked at uniform rods, so we always took that centre of mass to be right at the midpoint. If a rod is non-uniform, then the centre of mass will not necessarily be at that midpoint. So it might not be the case that we can simply just represent that force right at the centre of that rod. So a couple of examples that we're going to look at in this video. So Sam and Tamsin are sitting on a non-uniform plank AB of mass 25 kilograms and length 4 meters. The plank is pivoted at M, the midpoint of AB. The centre of mass of AB is at C, where AC is 1.8 meters. Sam has a mass of 35 kilograms, Tamsin has a mass of 25 kilograms and sits at A. Where must Sam sit for the plank to be horizontal? So we're told that Tamsin has a mass of 25 kilograms and sits at A, so this must be Tamsin here. And since her mass is 25 kilograms, her weight, the force acting downwards, will be 25g. We've got Sam here who has a mass of 35 kilograms, so his weight must be 35g. These are in newtons. We also have the mass of the plank, which is 25 kilograms. Now, that rather than acting through the midpoint, we were told that the centre of mass is at C. So that weight is going to act through the centre of mass, and that is also going to be 25g. And finally, since our plank is resting on the pivot at M, there is going to be a reaction force at M. So our first stage is done. We've got our diagram drawn. So the next thing we're going to look at, now that we've added our forces to our diagram, we can consider the fact that if we're talking about the plank being a horizontal, our plank is in equilibrium. So our previous video we looked at equilibrium, and what that means is that the resultant moments in each direction will be equal, but also the resultant forces will be equal. So I can use that and say that the force going up must be equal to the sum of the forces going down. So 25 plus 25 is 50, plus 35 gives us 85. So I've got 85g. So the reaction at M must be equal to 85g. So the reaction at M is equal to 85g. So now I can take moments about A. We're trying to find the distance where Sam was sat, so I'll include that distance there from A to the point Sam is sat. I'll call that distance x. So if I take moments about A, moments about A, always useful to specify the point that we're taking moments about, either on your diagram, often by putting a cross there, that can tell us that that's the point we're taking moments about, or just writing it there is fine. So our moments about A in the direction which is clockwise. So clockwise from A, we've got 1.8 times 25g. So 1.8 times 25g. And also from point A, going clockwise, if we're pivoting at A, going clockwise is this force here. So that would be x times 35g. So plus 35gx, and that is equal to the moment in the anti-clockwise direction. So in the anti-clockwise direction, we've got the reaction at M, which we worked out to be 85G. And since we were told that M was the midpoint of AB, that distance must be 2 meters since the entire distance was 4. So I've got 2 times 85G. So we'll do a little bit of simplifying there. So 1.8 times 25G is going to give us 45G plus 35GX is equal to 2 times 85 is 170. So 170G. And now there is some simplifying I can do because every term involves G. So I can cancel out by dividing everything through by G, and that's going to leave me that 45 plus 35x is equal to 170. If I subtract 45 from both sides, I get 35x is equal to 125. So x is equal to 125 over 35. That's 25 over 7 if we're writing it in its exact form, or x being equal to 3.57 meters. That's written to a couple of decimal places, and that there is our answer. So just to make that clear, we've asked where Sam must sit. So x is 3.57 meters. So Sam sits 3.57 meters from A. We'll just make that absolutely clear in our answer that that is the distance from A. We can kind of see it from our diagram, but it's useful again just to have that written there. Our second example. So we've got one that this time we've not been given diagram, so we're going to draw the diagram in there. So a non-uniform rod AB is 3 meters long and has weight 20 newtons. It's in a horizontal position resting on supports at points C and D, where AC is equal to 1 meter and AD is equal to 2.5 meters. The magnitude of the reaction at C is 3 times the magnitude of the reaction at D. Find the distance of the center of mass of the rod from A. So this time they haven't given us the center of mass like they did on the first one. We're being asked to find the distance of the center of mass from A given those pieces of information about the rod and about the reaction forces. So if we start with our rod of length 3 meters, so rod of length 3 meters, we're told it has a weight 20 newtons, so we'll add that in just a moment. It's resting on supports C and D, so the rod was A, B. Resting on supports at points C and D, where AC is 1 meter, so the distance from A to C is 1 meter, and AD is 2.5. Well, if the entire length of the rod is 3 and AD is 2.5, that must mean that D is 0.5 meters from the end. So we've got D being 0.5 meters from the end. Again, we were told the weight was 20 newtons, and we're not told we're told it's a non-uniform rod, so our weight isn't going to act directly in the center. It's going to act rather through the center of mass, which might not necessarily be the midpoint of the rod. So we'll draw that somewhere here, and the weight is 20 newtons. It was a weight we were given rather than a mass, and the distance from A is what we're trying to find there, so I'll call that distance x. Finally, we've got the reaction forces at the supports. So we're told that the magnitude of the reaction at C is 3 times the magnitude of the reaction at D. So the reaction at D, I'll write as reaction at D, RD. The reaction at C was 3 times that. So rather than writing RC, I'm just going to say that that is 3 times the reaction at D. So I've got 3 lots of the reaction at D. Now, we're going to use the fact that since it was resting in a horizontal position, the resting is important as well. That tells us it's in equilibrium. So that means the forces in the upwards direction are the same as the forces in the downwards direction. So I've got 3RD plus RD. So in total, I've got 4 lots of RD, and that is equal to 20 newtons. That's the force acting downwards. So if 4RD equals 20, I can divide through by 4 and get the reaction at D being equal to 5 newtons. So the reaction at D is 5 newtons, which means the reaction at C, which was 3 times that, must be 15 newtons. So I've got the reaction at C and the reaction at D. So now I can take moments about A to find that distance there. So if I take moments about A, we're taking moments about A in the direction which is anti-clockwise. I've got 1 times 15, the force 15, the distance 1. So I've got 15 times 1. And I've also got, if I'm using A as my pivot, I'm also using the fact that I've got 5 being multiplied by this distance, which must be 2.5, since that's 0.5 and the uniform rod had a length of 3 meters. This distance must be 2.5. So 15 times 1 plus 5 lots of 2.5, and that is equal to the moment in the clockwise direction, which is that distance x times 20. So 20x. Doing a little bit of simplification, 15 times 1 is 15, 5 times 2.5 is 12.5. That is equal to 20x. Adding these two together gives us 27.5. So 20x is equal to 27.5. So to find x, I can do 27.5 divided by 20, and that's going to give me 1.375. So we can say that the centre of mass is 1.375 meters from A, and that there is our final answer on that one. That's the end of this video. Thank you so much for watching. For more A-Level and GCSE maths content, like and subscribe to N Jackson Maths on YouTube.